Systems of equations, one of my favorite things in all of Algebra 1. So, we've graphed linear graphs before, y equals mx plus b, that kind of stuff. Today we're going to have systems of equations which pair up two of those equations. We're going to graph those lines and see where they intersect each other. So, a linear system of equations has more than one equation. Whoa! The solution of a system of equations are any points that the equations have in common or points that they share. So it's where they intersect, where they cross each other. It's very fun. Oh man, you're in for a real treat here. All right, here we go. We're going to graph y equals 2 and y equals x plus 1. Now remember, an equation like y equals 2 is just a flat line at 2. So you go up 2. Whoops. That's not a straight line. That's where rulers are nice. There we go. We graphed y equals 2. Now we're going to graph y equals x plus 1. We start with the y-intercept, which is 1, and then we use our slope to find the next point. The slope is 1, or 1 over 1. So we'd go up 1, right 1, up 1, right 1, up 1, right 1. And you can keep going up 1, right 1. The big important thing is we're looking for the point of intersection. So they cross each other right here. Now that coordinate is 1, 2. That's your solution. You're looking for where they intersect each other. How could you check this algebraically? Well, you could substitute in 1 for x, 2 for y, and make sure it works. If we substitute in 2 for y here, you have 2 equals 2. Great, it works. You substitute them in for x and y here. Y is 2, x is 1, 2 equals 2. They both work. Unbelievable. Look at that. If you got some extra time on a quiz or test, substitute the coordinates in for x and y and double check that they work. We're going to graph x plus y equals negative 2 and 2x minus 3y equals negative 9. Now, you got some options here. These are in standard form. You could graph them in the form that they're in, or you can move them around and get them in the slope-intercept form. The choice is up to you, whatever you like doing. So, me personally, I like to get them in the slope-intercept form because then it's easier for me to find my points when I do that. Because when I do standard form, it's like if my line is not perfectly straight with a ruler, it can get a little dicey. So let's try that on one of these equations, and then the other one we'll graph it in the form that it's in. So if we look at x plus y equals 2, negative 2, and we're solving this using intercepts. Remember, it's like if you substitute in 0 for y, I'm left with x equals negative 2. And we don't even have to solve it. That's done. So our x-intercept is negative 2. If we substitute in 0 for x, we're left with y equals negative 2. So graphing this in standard form, we found our intercepts. The x-intercept is negative 2. That would be left 2. The y-intercept is negative 2. That would be down 2. And then you would want to draw a perfectly straight line through these points. Now, that's hard on the board. I don't have a ruler up here. But you could check the slope from left to right. That's down 2 over 2. And if the slope is negative 2 over 2, that really means our slope is negative 1. So we could just take any point and go down 1, right 1, and make some more points. You could also go up 1, left 1. Or just use a ruler and make sure your line is super duper straight. So that was graphing it in the form it's in. Now you could totally do that with the second one too. That would give you, and we're not going to do this, we're going to move it around, but it would give you 2x equals 9 and negative 3y equals negative 9. You divide by 2, you get 4.5. You divide by negative 3, you get y equals positive 3. Now the reason I don't like that is because 4.5, I can do my best to find the middle-ish, between 4 and 5. It'd be like here-ish. But like, that might be 4.6. And it's like, will that impact my graph? It could. So I don't like graphing it in standard form when we're trying to find a point of intersection. So this is where I get it into slope-intercept form, which means get y by itself. So if we're sending the 2x to the other side of the equal sign, are we going to add it or subtract it to move it over there? We would subtract it. Minus 2x minus 2x. So we'd have negative 3y equals negative 2x minus 9. Now we can't have negative 3y. So we'd have to divide everything by negative 3. That would give us y equals negative 2 over negative 3. The negatives cancel, so we have 2/3 x. And then negative 9 divided by negative 3 is positive 3. So if we're graphing that, we would start at 3, our y-intercept, and then our slope is 2/3. So we would go up to right 3, up to right 3, up to right 3. You could also go down to left 3. Ooh! There we go. We're looking for that point of intersection. They cross right here. That's to the left 3. So our x would be negative 3, and then it's up 1. Negative 3, 1 would be our answer. You could check that algebraically in both equations. Let's see, negative 3, 1. So the x is negative 3, the y is 1. Negative 3 plus 1 is negative 2, so that one works out. If we're checking this one, 2 times x, 2 times negative 3, minus 3 times the y. Let's see, this would give us negative 6 minus 3, and that is negative 9. Sick, dude. Look how smart we are. Look how smart. Give this one a try. You got y equals negative 2x plus 6. For that, you would start at 6. 1, 2, 3, 4, 5, 6. The slope is negative 2, so you would go down 2 over 1. You could do that a few times. You could also go up 2, left 1 a couple times. There we go. Now the second one is in standard form. You could graph it in the form that it's in, but I would recommend getting it into slope-intercept form. So we'd have to add the 14x to the other side, which would give us 7y equals 14x plus 14. And we don't want 7y, so we have to divide everything by 7, which would give us y equals 2x plus 2. You start at 2. And then you go up 2 over 1. Yes, that's where they intersect each other. Could go down 2, left 1. But really the point that matters to us is that point of intersection, which is right here at 1, 2, 3, 4. 1, 4. You could verify that algebraically. In the originals, let's see, y equals negative 2x plus 6. That would be negative 2 plus 6, which is 4. That one worked. The other one, 7y, 7 times 4 minus 14x equals 14. Now, I'm checking it in the original. Hopefully, this equation in green is correct, but I like to go with the original usually because they gave us that. I might have made a mistake over here, so I trust their work more than I trust my own just because sometimes I make mistakes. So this would give me 28 minus 14, which does equal 14. So we're good. 1, 4 works. How fun. All right. Now we do have these special systems of equations. You might have some parallel lines, which are lines that have the same slope but a different y-intercept. Now, if we were graphing them, they might look like this. Those are lines that have the same slope but different y-intercepts. We're looking for where they cross. Those are never going to cross. So if our solution is where do they cross, and it's not possible, we're going to say no solution. So if you have parallel lines, there's going to be no solution. There's another one, perpendicular lines. The slopes are the negative reciprocal of each other. Now that's not super important because, I mean, when you have perpendicular lines, they form a 90-degree angle. Okay, whatever. They're going to cross at one point. That's all gravy, baby. The other weird one, though, so that one isn't even like that special. The other weird one is these coinciding lines. So you graph the first line, and it looks like this. And let's say the other one is in a different form, and you graph it, and it perfectly overlaps. If that's the case, and we're looking for where they cross each other, they're always crossing each other. So we say IMS, which stands for infinitely many solutions, because there are infinite little decimal coordinates on those lines. They're the exact same line. And usually one's like in slope-intercept, the other's in standard form. But if you moved the standard form into slope-intercept, it works out to the same equation. So those are the special ones. We got a couple of those. All right. Again, I like doing these in slope-intercept form. I feel like I make less mistakes when I do that. So this first equation, we would add the 6x to the other side, which would give us 2y equals 6x minus 8. Now we have to divide by the 2, which will give us y equals 3x minus 4. If we're graphing that, you start at negative 4, 1, 2, 3, 4, and your slope is 3, so you'd go up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1. You could also go down 3, left 1. And look, I like this better because if you were doing intercepts, if you were solving for the x-intercept, it's going to come out to 8 over 6, which is like 4 over 3. And you don't know exactly where that is if you're graphing. So then it's just kind of like an estimate, which is fine, but we're looking for exact answers. So I would highly recommend you get them into slope-intercept form. There's our first line. The second line, we just have to add the 3x to the other side, which would be y equals 3x plus 7. We start at 7, 1, 2, 3, 4, 5, 6, 7. And then our slope's 3, up 3 over 1, or down 3, left 1. We're looking for where these lines cross each other. They never cross each other because they are parallel. And you would know that because they have the same slope, but different y-intercepts. So, if they never cross, we say no solution. And we're having fun. Look at us having fun. Oh yeah. I think there's one for you to try, but we're just going to do this one together. And then this is it. So graphing this first equation, first of all, we're going to send that 3x to the other side, which will give us y equals negative 3x minus 1. You start at negative 1. Your slope's negative 3. That's down 3 over 1, down 3 over 1, down 3 over 1. Up 3, left 1 as well. The second equation, you move it around a little bit. You could add the 9x to the other side, which would give us negative 3y equals 9x plus 3. And then we would divide everything by negative 3, which would give us y equals negative 3x minus 1. You might notice that's the same equation we got over here when we adjusted it. So it's going to be the exact same thing. You'd start at negative 1, you go down 3 over 1. It's the exact same line. They perfectly overlap each other. So that's where we say IMS, which again stands for infinitely many solutions. Now you could always just write IMS in this class. You don't need to write infinitely many solutions. Look, that's it. We just graphed some systems. How cool is that?